Hello, everyone, and thank you for joining us today. We know you're very busy with multiple to-dos to complete today, and I really appreciate you taking the time to spend the next 60 minutes with us. Today, we will look at an in-database machine learning solution for real-time recommendations. And we hope you will find this presentation to be both interesting and informative. My name is David Ronald, Director of Product Marketing at TigerGraph, and I'll be your host today. And I'm joined by two colleagues, Mingxi Wu, VP of Engineering. Mingxi has a long and esteemed illustrious history with TigerGraph, 19 years in data management industry and research. He has a BS in computer science from Fudan University and an MS and PhD in computer science from the University of Florida. I'm also joined by Shengran Liu, who is solution architect at TigerGraph. He has a BS in engineering from Tsinghua University, a master's and a PhD in mechanical engineering from Stanford University, just down the road from us. And his PhD minor was in philosophy. And he focused on applications of mathematical logic in artificial intelligence. So undoubtedly, he's a very intelligent guy, as is Mingxi. Before we get started, a few housekeeping issues. We want to hear from you, but the phone lines are muted. No surprise, I'm sure. That's standard practice. Please use the Q&A button in the Zoom panel to submit your questions. We hope this webinar will be interesting, and as a result, you'll have many questions for us, and you can submit questions at any time. The webinar is being recorded and will be uploaded to our website shortly after it concludes. And additionally, you will receive an email with the URL to the archive very soon. If you have any issues with Zoom, don't hesitate to reach out to us, and we'll do our very best to resolve them as quickly as possible. And with that, I'd like to pass control of the webinar to Shengran.
So we first gave the motivation of why we want to do machine learning in graph database. And then Changran is going to give a demo and a deep dive on how he implement recommendation solution in our TigerGraph database. And then he will give a technical presentation on how the model works and what are the intuition and the implementation steps. So before we start, I want to review how the current data scientists are doing machine learning from different data sources and how the whole process look like. Suppose you have a data management software to manage your data, and you use it to store, update, and pre-process your data for different tasks. And most likely, you are going to use a database management system, since it has been proven that it's very handy for different reporting tasks and easy analytic tasks. And also, you may also use NoSQL key value store to do point data lookup. And this database technology are very good at generating reports and doing slice and dice to group by your data and show some aggregated results. But they are not very good at complex data analytic tasks, such as machine learning. So what do people do today? They usually ETL their data, extract, transform, and load their data into the database management system. And when they do want to do a machine learning task, what they do is they use the SQL language to generate features and then send the data to a specialized machine learning platform, such as TensorFlow, Spark, RStudio, MATLAB, etc. And they do the machine learning training there And then after the model is learned and validated, they import the model parameter back to the database or some server to activate the model. So when it's time to refresh the model with the latest data, the whole process has to be started over again. And let's take a closer look how the data journey looks like. At the beginning, the data is training data is extracted and transformed to the machine learning platform. And the data is already stale when it's used for the machine learning task. And usually, most machine learning platform are single node with specialized hardware, such as GPU, high memory, and multi-cores. They usually are not very good at scale up and scale out because the machine learning is so hard and they focus on solving the problem on the single node first. So after seeing the whole data journey, we can see there are disadvantages of doing machine learning tasks outside the database. So what are the challenges that we do the machine learning within the database? So we know that most machine learning is computation intensive, but they are most likely parallelizable. And most databases are designed for simple ad hoc queries, but most databases are good at the parallelization and scale out and scale up. And also, most database is using the de facto standard SQL, and it takes a lot of efforts for the SQL for database to use SQL to solve simple machine learning tasks. And some databases are good at the data warehouse workloads, and they are not mutable, and data are loaded and updated at night. So these are the three challenges for in database machine learning. And facing this challenge, and we know that there are advantages to do machine learning inside the database. So how can we do this by the latest technology? So one solution is we can do in database machine learning with GCQ in graph. And graph is a native graph storage and support the property graph model. And also graph has a powerful language GCQ, and user can declaratively write any algorithm from simple reporting to advanced analytics such as machine learning algorithm. And the engine will automatically scale out and scale up the query processing part. And also graph support real-time update, meaning that you can ingest data and mutate your data at any time. And also with the real-time update, you learn machine learning model parameter can be inserted as attributes of the objects, and you can serve the activate your model in place of the data habitat. And as I said, SQL is the de facto standard for relational database, and it has limitation, and it's not suitable for machine learning tasks. But GCQ, which is the flagship product of graph API, it is designed for property graph data traversal and advanced analytics, and it's good at pre-processing your data, and it can help machine learning doing the model training by the ingredients such as flow control, while loop, and it has runtime state variable accumulator, and it also has the pattern match declarative building block to help people to easily specify what data they want and what data they didn't want. And the model validation can also happen within graph due to the real-time mutation support. So with all these components within the graph database, we are ready to see how we can do machine learning within graph. And now I'm going to pass the presentation to Changran, who is going to give a concrete example how we do machine learning task within graph. Changran.
Hello, everyone. This is Changran. First, I want to thank Mingxi for sharing with us the insight he has of the motivation to do in-database machine learning. So today, I'm going to show you an example to demonstrate the Tiger Graph's capability to do in-database learning. And specifically, I'm going to choose the recommendation system as an example. And the reason I chose this example is actually nowadays, you can find the application of it almost everywhere. Say if you go to those media websites, such as Spotify or Netflix, and they will recommend the music and the movies that you may like. Also, if you go online shopping, like Amazon, and you can see Amazon will also recommend the items that you may be interested in. Even you search on Google, you can also find that Google will also show you the related topic that you may be click on. So actually, the performance of the recommendation system can directly link to the profit of a company. Actually, in October 2nd, 2006, Netflix started the Netflix prize competition that offers $1 million prize to the winner who came up with the best algorithm that can best predict and then recommend the movies to the users. So how does recommendation system work? So now let's use this movie recommendation system as an example. Say if you go to a movie review website, this is typically what you will see. You can see some information of the movie. And you can also see different users give different ratings to the movie. So in a nutshell, how the recommendation system works is it will based on the information of the movies and the user's rating. And then it will try to make prediction of the rating for the users. And at last, it will recommend the movies that has the highest predicted rating. So now let me use this simple example to give you more intuition of how different recommendation methods can predict the movie rating. So first, I actually also want to say that to represent the user rate movie relation, you can have different ways, but I always find that graph is the most intuitive way. So that's what I'm going to use today. So in this example, we have two movies represented as two vertices in the graph. And for each one of the movie, there are also some information, like this Toy Story is tagged as Disney movie, and the Iron Man is tagged as Marvel and also action movie. We also have two users and some background information of the user. We see here, Alice rated the movie Toy Story 5 out of 5, and Bob rated Toy Story 4.5 out of 5, and he also rated Iron Man 5. And in this example, we want to predict what the rating that Alice may give to Iron Man. To make such prediction, one of the most intuitive way is to first check the information of the movie. Say in this case, we know that Iron Man is actually a Marvel movie. And then if we go to the information of the user, we can also find that Alice is actually a fan of Marvel movie. So in this case, we may say that Alice is very likely to give a high rate to Iron Man. And this type of method is called the content-based method. So it's mainly relying on the user profile and the movie feature information. So this method is quite intuitive and also quite reliable when we have enough information of the user and the movie. However, what if we don't have those information? So in this case, there is another type of method. It's called the k-nearest neighbor. And here is the intuition of this method. In this case, say we only have the rating record of the user to the movie. But if we look at Alice's rating to Toy Story, we find that, okay, it's a very high rating, so Alice may like this movie. And we can also see that Bob also gave a high rating to Toy Story. So based on this evidence, we can say that it's likely that both Alice and Bob share a similar taste of movie. Now, we look at Bob also have another high rating for Iron Man. So based on our evidence, we can say that since Bob liked Iron Man, there's a high chance that Alice may also like Iron Man. So this type of method does not rely on the user background information. It only relies on the rating record. And it also works quite well if we have enough of the rating record. However, what if the rating record is very sparse? In this example, say, if Bob did not read Toy Story before, what happened? So if you look at this example now, it will be very difficult for us to justify using Bob's rating to Iron Man to predict Alice's rating. So in addition to above two method, there's another type of method called latent factor method. And this is actually a model-based method. So it actually has a stronger flavor of machine learning. What I meant by that is not that intuitive, and it may also seem kind of mysterious to some extent. But basically what it does is for each one of the user and the movie, it will try to compute a vector, embed it with a vector. And hopefully this vector will capture some feature of the movie and the user. And in the end, it will use the dot product of a movie and the user as the predicted rating. So far, it may still not clear enough to you how does this method work, but don't worry, I will actually go through an implementation of this method step by step with you and make sure everybody know how to implement this using Tiger Graph. So now that I've covered several different methods, and you may also notice that each one of the methods has some pros and cons. So one very straightforward idea to further improve the performance of the recommendation system is just to combine some of them together, right? So here comes the hybrid method. But we know that when we trying to have a hybrid method, the part of content-based method can be done easily just by looking up some information of the user and the movie. However, when we are trying to implement the model-based part of the method, this actually requires us to train a model, which is also known to be quite computationally intensive, and it can be a challenge for database, as Mingxi pointed out at the beginning. So today I will actually focusing on this part and show you how to implement some query to do in-database training. So now before I show you the detail of my implementation, let me show you very quick what this recommendation system is going to look like in Tiger Graph. So here I am showing you the schema of this recommendation graph. So for those of you that are not quite familiar with Tiger Graph, what a schema do is it will tell the database what types of vertices and edges you have in this graph and what information you want to put on those edge or the vertex. And this is actually defining the schema is the first step you need to do before you can load the data or start writing the query. So in this schema, we have in total 4 different vertices. Actually, this schema is built for a hybrid recommendation system. So some of the vertex are only used for model-based method, and some of those are only used for content-based method. And today I will mainly focusing on the model-based method. So if you look at this user vertex, here we will actually put a user ID as an attribute on it. And also you can see we have another list attribute called theta, and we will store the user profile vector that we want to compute in this attribute. And now if we go to the movie vector, here we defined 4 attributes on this vertex. The first one is the movie ID, and we will also put the movie name here. And the third one is the averaging rating of this movie. And at last, it's also a list. It's called X. And so in the end, we will also put the movie feature vector in this list. And between the user and the movie is an edge called rate. So it has 3 attributes. The first one is the rating that the user gave to the movie. And the second one is a label. So later we will use this attribute to label the data that we are going to use for training our model. And the last one is the prediction result from the content-based model. And also you see 2 other vertex, tag and term. Those are also only used for the content-based model, which we probably don't have enough time to go through for today. So here is the schema. So after you define the schema, you can now load the data into the graph. And now let me go back to the slides and talk a little bit more about the data. So this is the data we have. So this is the data I use today is actually some real world data. So it's from a website called Movie Lens. So in this data set, there are altogether 100K ratings and 40K tags that 1,000 users gave to 70,000 movies. And for each line of rating data, we have the user ID, the movie ID, and then the rating the user gave to the movie, and also a timestamp. And each one of the rating is a number from 0 to 5. Okay, here actually I have already loaded the data. So from our UI, you can also see the total number of vertices and the edge we have. And as I said, we have altogether 100,000 rates for this example. And after we load the data, this is what the graph will look like. Actually, this is only a very small portion of data. And you can see for this movie, you can see the movie ID, the movie name, and at last you see the X that we will be using to store the movie feature vector. And now it's empty because I haven't run the query to initialize it yet. And you can see this movie is rated by many users. And on the user vertex, you can see the user ID and also the user profile vector theta. Now it's also empty. And you can see here the rating that the user gave to the movie. Okay, so now we have all the data we need to build our recommendation system. But before we can actually get our recommendation, we'll first need to train the model. So to train the model, the first step, if you are familiar with machine learning, the first step is to initialize your user and movie vector with some random value. And this can be done using this initialization query. And this query actually allows you to specify the length of the vector you want to use as the latent vector. So here, let's say we use 19. So now this query is done. So after the initialization, we can now go to training the model. And the training part is done by this query. So here, actually, I have many more queries here, but some of those are used for the content-based method that we will not cover today. So this training validation is used for training the model-based method. And here, you need to specify the learning rate, the regularization factor, and also the number of iterations you want to do to train the model. So now if you run this query, so this takes less than 10 seconds to run. So at the end, it will output the accuracy of the model for each iteration. So actually now let me go back to the slides again and explain this output a little bit more. So in this example, I chose the root mean square error to evaluate the accuracy of the model. So basically, this is the equation to compute the root mean square error. In this equation, the Yij is the rating that user I gave to movie J, and Y hat is the predicted value. So inside this parentheses is basically the difference between our prediction and the real value. And after that, we'll take the square, and then we will compute the mean of those square error. At last, we'll take the root of it. So that's why we call this root mean square error. So basically, this gives you the overall error of your prediction. And the smaller this error is, the more accurate the prediction is. Now, if we go back to the output, you can see that at the beginning, before we start training our model, this error is above 1. So here on the first line, this is the root mean square error for the training data. And the second entry is the error for the validation data. And at the beginning, they're all above 1. And as we keep training the model, you see both of the error goes down. And here you can already see that both of the error goes below 1. So now that we have trained our model, we can further test how well this model works. And this can be done using this test query. So what this query do is, here you can specify a user by its ID. Say let's use 10. And if you run the query, it will show you the rating that this user gave to the movie and also the predicted value. So here, this user actually rated the movie with movie ID 155 before, and the rating he gave is 4. And our predicting value from here is the content-based model is here. And the last, this is a prediction from our model-based method. And you can actually see that for many of the movie, our prediction is actually quite close from both the content-based method and also the model-based method. And the prediction are actually around 20%. So now that we are satisfied with the accuracy of the model, we can now come to our final goal, which is actually to generate a recommendation for the user. And this can be done using this recommend query. So to run this query, it's quite simple. You also just need to specify a user ID. So let's say we use 12. And if you run the query, it will just show you the top 10 movies that this recommendation made to this user based on the content-based and also the model-based result. So first you see is the movie recommended by the model-based method. And those are the top 10 movies. You see the movie name and the ID. So the second part also shows you the movie recommended by the content-based model. So if you are careful enough, you can actually see that some of the movie are actually both recommended by both of the methods. This actually, to some extent, cross-validates the prediction result. So at last, let me show you more results that I tested using this system. So here I'm showing you the overall error for different type of methods. So if you are only using the content-based method for this set of data, we can get in the end about 0.91 RMSE value. And if we are only using the model-based method, in the end, we can get about 0.97 square error. But if we combine both of these methods together and build a hybrid model, in the end, you can see that the error is lower than both of these methods. And this is why we want to do in-database learning, as Mingxi pointed out at the beginning. So I know that I just ran a bunch of queries, and now you may be very curious what's actually inside those queries. So now let me show you the detail of the implementation. So first, just a little bit more about the intuition of the latent factor method. So in this example, we have 6 movies and 4 users. And in this table, those ratings are also, the number are the rating that the user gave to the movie, and the question mark is the rating that we want to predict. So before we actually see how does latent factor model do, let's just use some of our own intuition to see what we may predict those values. If you look at Alice's rating, we find that she likes the movie Love at Last and also Romance Forever. And if you happen to watch those movies, or you just looking at the name of those movies, you can tell that these 2 movies are actually romantic movies. And also, if you look at the last 2 lines, it seems Alice does not like sword versus karate or nonstop car chases. And you can see these 2 are actually action movies. So from this, we can say that Alice is actually a fan of romantic movie, but she's not a big fan of the action movie. Now, to predict the Alice rating to Cute Puppy of Love, now we know that Cute Puppy of Love is actually a romantic movie, so Alice may like this movie. However, Toy Story actually has more action content than romance content, so Alice may not like this movie. So this is very intuitively how we will predict the rating. However, our recommendation system does not have those background information. So how does it do the check? So the idea of the latent factor model is you will try to come up with a set of vector for each one of the user and the movie. So say in this case, this is the vector we have. So actually I will go into detail of how to compute those vectors, but now let's just assume this is the vector we get at the end. And after that, this method will use the dot product of the vector to predict the rating. So in this case, the predicting of Alice rating to Love at Last is the dot product of theta1 and x1. And the values here is actually 4.5. And you can also see the other prediction here. Okay, now if you look at this prediction, it's actually quite good, right? So if you compare the real value and the prediction, you see they are all quite close for the romantic movie and the action movie. And now, even if you look at those movies that need to be predicted, the prediction is also close to what we expected. Say for the Cute Puppies of Love is high rating, and then Toy Story is quite low. So how does this set of vectors does the trick? Now, if you look at the vector on the movie, you can see that for those romantic movie, the first element is quite high. It's much higher than the second one, right? Now, if you look at the vector on the action movie, you will find that the second element of the vector is quite high. Now, on the other hand, if you go to the user's vector, you find that for the romantic movie lover, the first element is high. And then for the action movie lover, the second element is high. So the intuition of this method is it will try to come up with, try to compute a set of vector that each element of the vector will capture some feature of the movie or the user. So in this example, I only use the vector of length 2, but actually it can be 10 or 100. And in the demo, actually I use 19. So usually the more features you have, or the more feature you want to capture, the longer the vector you want to use. But there's also a trade-off. Too many features can also cause overfitting. And the reason why this is called the latent factor method is because when we are computing those vectors, we actually don't know what does each element represent. And also, we also don't need to know what each element represents. This is actually a very typical feature of many machine learning methods. So now let me show you, let's review very quick the schema we need to use to implement this latent factor model. So schema is quite simple. We only need two vertex, user and the movie. And on the user, we will have a list theta to store its user profile vector. And on the movie, we have a list x to store its movie feature vector. And the rating is stored on the rate edge. And this is what the graph looks like after we load the data. And for those movie that has rating, we'll create edge. If the user does not read the movie before, those two nodes will be disconnected. Okay, so now here you see the flowchart of the query to train the model. So if you are familiar with machine learning, this is actually a very typical process for any optimization problem. So the overall picture is we want to find a set of vectors that can minimize the error between the prediction and the real value. So to start, we will split the data into the training and the validation set. And the second step is to run this initialization query to initialize the latent factor vector. And then we will have another query that I show you in the demo. And this query will have a while loop. And inside this while loop, it will first compute the difference between the prediction and the training and the real value. And then it will check if this prediction is good enough. If it's not good enough, you will use the gradient of the vector to update. So this part is done using a gradient descent algorithm. And then we'll keep this iteration and update our vector. And in the end, we will break this while loop once the result converge. So this part is actually the core of this training algorithm. And now what I'm showing you is the script that I use to train this model. And you can see that we only need less than 10 lines of GSQL code to implement the in-database machine learning model. And now I will actually go through line by line with you and make sure everyone knows what each line do. So on the left is the code I wrote, and you can also see the variables in the code in the script is color coded. So for all the variables on the user end, the color is the same as the vertex showing here, and also for the movie. And on the right is the example we used for this. And let's say now we have already initialized our latent factor vector, and those are shown here on each one of the vertex. So the first line in this block is to activate all the edges between the user and the movie. And then in this accum block, what we will do is to compute the gradient of the user vector and also the movie vector. So in Tiger Graph, all the code in this accum block will actually be parallelized. Now in the first line here, this simply does the prediction. As I said, the prediction is obtained by calculated using the dot product of the user vector and the movie vector. So here the results are also shown on this example here. And the second line is to compute the difference between the prediction and the real value. And this is what we will have after this line, all the delta value. And the next line is to compute the gradient of the user vector. And this is done by summing up all the product between the movie vector and the delta value. So those are the results we will have for this example. And in the last line, we will compute the gradient of the movie vector. And this is done actually similarly by summing up the product of the user vector and also the delta value. And this is the result you see here. Now that we have all the gradients, we'll move to the post-accum. And here we will use this gradient to update our vectors. So this is actually also quite straightforward. So this line, we will update the user's vector, and this line will update the movie's vector. So those are the theta prime and the x prime value are the vector that's updated. Now, if we plug this updated vector back into our prediction, you can see that now only with one iteration, we already have better prediction. And this is manifested by the updated delta value. You see the new delta prime are all smaller than the previous delta in absolute value. So now I hope after this example, you can see that first is the user rated item data relation is essentially just a graph, and the whole training can be done by passing the information between nodes that connects together. And you only need less than 10 lines of GSQL code to achieve that. So now let me summarize what we have today. So first, in this webinar, we show that the user rate item data relation is essentially a graph, and we can load the rating and tagging record into the graph using tag graph. Actually, when we load the data, we are essentially storing a sparse matrix using a graph, which can greatly compress the data. And second, I also show that training a latent factor model can also be solved by passing information between connected nodes. So it can be treated as a graph problem. And this is why we said at the beginning, many machine learning problems should be actually better solved using graph. And this is because both the training data as well as the model can be well represented using graph. And also, if you consider the large data size of machine learning problem, you will see that why we think graph plus database is a natural solution for many machine learning problems. And third, even I did not have enough time to cover the hybrid model, but for the demo, it can actually be easily implemented using tiger graph. So we actually see tiger graph has the capability for real-time model update without having to export the model or the data to a machine learning platform. And lastly, I also want to point out that with only very minimum amount of work, this solution can also be applied to many other applications like link prediction or entity resolution. So with that, I would like to conclude and take the questions.
Thanks, Shanran. That was a fantastic presentation. And hopefully everybody in the audience learned a lot from it. I would like to remind everybody in our audience today that you can submit questions using the Q&A feature in Zoom. So if you haven't already submitted questions, we do have 2 or 3. If you have a question first and you haven't yet submitted, please do so now. We have a few questions from the audience. The first one is, how do you manage the life cycle of a model? Do you retire a model?
Yeah, this is Mingxi. I can take this question. So as this example has shown, that Changran actually stored the model as the vertex attributes in place of where the data is existed. And then during his iterative training to use gradient descent, he actually updated the model parameter in place. So the vertex, he's trying to learn a latent vector for each user and for each movie, and he just keep updating the attributes, the model attributes for those entities. And so this model management is actually just like you manage additional attributes or additional vertices inside the graph database. And when you use it, you can handily access them and use them. And to refresh them, it's just like another attributes or vertex update. So it's very timely and it's very convenient to keep in sync the data and the model inside the tiger graph.
Great.
Thank you for that, Mingxi.
Thank you for that, Mingxi. Another question is, how fast is the training?
This actually, tiger graph is implemented as a MPP architecture and using C++. So it explores the hardware as much as possible. So if you have multi-cores, and it uses all the cores to do parallel computation. If you have multiple machines, it uses all the machines to shard the data, and then it uses all the cores on those machines to parallel doing any query processing. So it really depends on your hardware, and we achieve the optimal processing time. So in this example, Changran shows he is training a couple thousand edge data and then using 10 seconds for 100 iterations. So it's fast.
So we have another question asking, are there code or data example available on Tiger Graph Cloud that the developer can access to use them? So for now, we haven't have a cloud environment set up for the machine learning problem yet, but we are considering.
You can put this code in GitHub.
Yeah, but yeah, and also all the script and the slides in this webinar will be uploaded after the webinar.
Perfect. Thank you
Perfect.
for that, Shengran.
Thank you for that, Shengran. Another question is, besides latent factor model,
which obviously you can do
with GSQL,
what other model can you do with GSQL?
That's a good question. So actually in our Graph Guru 22, I also did a demo of using TileGraph to implement a neural network that's able to recognize some images. So actually, so that's so far 2 implementation we have, but GSQL is actually capable to do more than that. And basically, most of the machine learning problem that can be represented as a graph can be done using GSQL. So here I got another question. Is it possible to get a comparison of Tiger Graph deep learning feature set against other primary platforms like TensorFlow and Keras? So, good question. So actually, internally, we are trying to do some benchmark between the Tiger Graph's performance with other machine learning platform. But also, as Mingxi pointed out, so Tiger Graph use MPP. So basically, all the so the training can be done distributedly and also in multi-threads.
Okay, thank you.
Okay, thank you.
I think there's one more question.
I think there's one more question.
What about when there
What
are
about when there are
multiple
multiple attributes
in the model?
In the model?
So actually, that's the part I did not have enough time to go through today. So for our hybrid model, we actually use both the attribute obtained from the model, from training, and also from the content as to use for our prediction. So this is also not a problem for Tiger Graph.
Okay, great. Okay, great.
Thank you. I
think that's all the questions we have. I think we'll move on and wrap up the webinar. Okay, great. Fantastic. So, questions for us which haven't been answered by either of my colleagues, Changran or Mingxi, please reach out to us. There's a couple of easy ways for you to do that. One is to join our developer forum at the URL shown here. It's a lengthy one. When we send out the URL to the presentation later, you'll have a chance to look at that URL and click on it and join the forum. Or you can sign up for our developer office hours, something that we do every Thursday at 11 o'clock Pacific time. And that usually lasts for about an hour or so. And that's a great opportunity to have an online one-to-one interaction with one of our subject matter experts. There are multiple additional resources. We're always adding more things to this list. We encourage you to try Tiger Graph for yourself, and probably the most convenient way to do that is to go to Tiger Graph Cloud. So that's tigergraph.com/cloud. It takes just a few minutes to register and to get started. We have a free tier, which I think is very important. Free in perpetuity, so you can begin to explore and experiment with Tiger Graph free of charge. We have a variety of demos, which we call test drive demos, at that URL shown there, /demo. You can also download the developer edition, and there's a variety of Guru scripts that we have on GitHub for you to leverage in your own exploration of Graph. And that brings us to the very end of the presentation. Hopefully you found this Graph Gurus webinar useful. We do these webinars pretty much every week on a Wednesday at 11 o'clock in the morning. The next one will be next week, Wednesday, the 5th of February. That one's a virtual roundtable, so online webinar or online roundtable with 3 participants. We have Chris Premisberger, Editor-in-Chief of eWeek, on that panel, along with Dan McCreary, Distinguished Engineer at Optum, and also Neil Gomez, formerly of Amgen and now the CEO of Convexa. And so the topic there will be healthcare and how graph database and analytics is being applied to transform healthcare in ways such as improving the quality of care while reducing costs, detecting fraud, improving member satisfaction, and more. So we hope you will join us for that. Additionally, the popularity of these Graph Gurus events has been such that we've now taken them on the road, as it were. We do a number of events called Graph Gurus Comes to You. We have one coming up next week in Seattle, a couple of weeks after that, mid-February in San Francisco, and we're doing one in Atlanta. And if you want to see a list of other events that are scheduled, you can click on the URL, tigergraph.com/Graph Gurus Comes to You. And additionally, and very importantly, if you would like to request that we come to your city, then please reach out to us. You can do that at that URL and request an event in your locality. We'd be more than happy to come out to your area of the country and meet with you and give a workshop. And that brings us to the end of the webinar. As I said at the top, we know you're very busy. You have many to-dos on your list today, and we're flattered and pleased that you've chosen to spend the hour with us. We hope that you found it informative and interesting. We're very passionate and enthusiastic about graph, and hopefully some of that enthusiasm, much of that enthusiasm perhaps has worn off on you. We hope our enthusiasm has been contagious. So that's it. Thank you from Mingxi, thank you from Changran, and thank you from me.